So this is a little note on the three-dimensional crystal and how we can determine the force constant matrix. And of course, once we know the force constant matrix for a crystal, we can work out from it easily by multiplying with the masses the dynamical matrix, and therefore by taking this dynamical matrix into the K space, performing the Fourier transform. Just remind you about this. So this is the Fourier transform basically of the dynamical matrix written in the direct space into the K space. So once we perform this transform, we can calculate the vibrational frequency by setting up the appropriate eigenvalue eigenvector problem. So if you have a GFT code and you consider a realistic system, then calculation with the force constant matrix can be done using the method we considered previously, this frozen phonon approximation we discussed before, or you can use perturbation theory, the density functional perturbation theory for that. But here I will just illustrate the construction of for a three-dimensional system of the force constant matrix using a very simple idea of a force field. So suppose we have a very simple force field, which is a pairwise interaction between atoms, as written here. So we have a sum over all atoms in the system, and this could be, this of course, we sum up over all atoms in the infinite crystal. So we will have to extract from here a part which is proportional to the size of the system. So we shall do this in a second. But the point is that if we are given this potential energy as a sum of these pairwise interactions between different atoms, this function here may depend on the types of atoms A and B, but it will depend only on the distance between them. So if we now allow atoms to move away from their equilibrium positions, so we have by RA naught we denote equilibrium positions, and UA will be atomic displacements. So of course this distance here, the vector of it, will be given as a vector in the equilibrium in the relaxed lattice, plus the difference of the atomic displacements. Then what we need to do, we need to substitute this in here and expand it with respect to atomic displacements. So this is a very simple mathematics, but I will just show it quickly, comment on these lines here quickly. So the potential between two atoms depends on the distance between them, and the distance between them is given as a distance R naught of the positions at equilibrium. And that is the absolute value of it. So basically, this is a square root of the difference of atomic coordinates. So we have to be rather careful here, yeah. But we can still expand it in the Taylor series. So we'll have a term, a constant term, which we're not interested in. There will be a linear term. This derivative is calculated at the positions R naught, and the harmonic term, and so on, which will only keep terms up to the harmonic term. The function phi depends only on the absolute value of the vector between two atoms, so only on the distance. So this derivative can easily be calculated. So the first derivative is, so we use the chain rule, so it will be f prime with respect to the distance itself, with respect to the absolute value of the vector, and then we have to differentiate the absolute value of the vector with respect to its component. We're writing the absolute value as the square root of the sum of squares of atomic components, and this is easily calculated, and we will get this result. Similarly, the second order derivative is worked out, and you obtain this result here, and you can also see that that derivative is explicitly symmetric with respect to the permutation of indices alpha and alpha prime of the directions. So once we have all the derivatives in place, we can substitute all these results in the expression for the potential energy. The linear terms would not contribute to the potential energy expansion because we calculate them at equilibrium, and we sum this up for all atoms in the system. Of course, we will arrive at the sum of forces acting on atoms at equilibrium, which is 0. So we only need to keep basically the second order terms. We still needed the first order terms to work out the second order derivative. So if you substitute all this in here, and remember this u in that expansion was actually the difference of UA and UB, you arrive at that expression where these second derivatives are given by that formula. And this can be rearranged a little. So you can have, first of all, a diagonal term in with respect to atomic numbering A, which contains this sum over the lattice for all atoms, excluding atom A. This prime means that B is not equal to A. And there will be another term in which A and B could be different, which contains this particular expression. So up to this point, the derivation was rather general. This could have been a molecule or periodic crystal. And that particular expression for the potential energy, as we worked out here, would correspond to harmonic expansion of the potential energy with respect to atomic displacements, which is valid for any type of system. Now, if we want to talk about crystals in particular, then we have to remember that A and B's, they correspond to two indices, the index L of the lattice vector and the index S of the atom within the unit cell, the basis. And therefore, we can finally write down the force constant matrix in this case. So we have here a diagonal term with respect to atomic displacements. So that diagonal term would contribute this term here. So you see the L, this should be L prime, L prime. So there will be a diagonal term here for L equal L prime and S equal S prime, and it contains a sum over across the lattice of this type. So we sum over all atoms B, which are given by double primed indices, excluding atom A, so excluding an atom LS. Yeah, that's why the prime here. And we take out the second derivative of that expression. And by the way, it's easy to see that that first of all, this force constant matrix does depend explicitly on the difference of the lattice vectors, as we proved before, if you remember, quite generally using the periodic symmetry of the crystal. That's the first point. The second point, if you look at this expression very carefully and sum, say, over L or L prime, you will find that the sum here would cancel out with the sum here. And remember, we also had this property before. I'll just show it to you so you would make a connection with this result. So this is that property we discussed previously, and that is indeed the case in this particular calculation. And that's another property we proved for the force constant matrix of a crystal.